Good afternoon, all. As we know, in the previous session, we were discussing about the field, capital E, for a line charge. This concept actually is linked to your charge distribution, that is rho. Okay, uniform charge distribution we have studied. There are three types of charge distributions. You know, it is regarding volume, surface, and line. Okay. In the previous sessions, we have seen how to derive or how to find the electric field intensity expression in case of volume charge distribution. When you have a volume charge distribution over certain field, then what is the electric field intensity? And in previous session, exactly just before this session, we have seen how to find the electric field intensity for a line charge. For a line charge, we have taken a long wire, okay, long infinite wire, whose thickness is very small compared to its length. Infinite wire we have considered, and we have taken a small portion of this wire. Considering that rho L as the linear charge density of that particular area of the wire, we found at point P the electric field intensity, and the same concept we applied to the complete wire by integration. We found out the electric field intensity expression. We have derived this E for line charge. Now one more is left out. In case of charge distribution, we have surface charge distribution, that is surface charge density rho S. I had shown you this, you just check it, for three different types of charge distributions. Okay, this is wire, this is some volume considered, and this is a sheet. In that sheet, some area we will consider. Okay, and for a volume charge distribution, if you see the final expression E has got rho V in the expression. Similarly, when you take this field of a line charge, you have in the final expression, if you see, we have solved this, rho L is there in the final expression. So similarly, in today's session, we are going to deal with the field due to a sheet of charge. That is, we are considering a sheet, okay, some infinite sheet, some part we will consider, and within this, because of this, say it is having a surface charge density rho S, let us see what is the field intensity capital E. Okay, so this will be the third one of the charge distribution, E due to surface charge distribution. One important thing, just to remind you, in a previous session what we dealt, it was for line charge. So while doing this, if you remember, the point considered was on y-axis, okay, and if you resolve the field, this is the resultant field direction, AR direction, the same direction field will be there, and these two are its components, EY in y direction and EZ in z direction. Okay, what was important here? Out of these two, if you just remember the derivation which we discussed in the previous session, out of these two components, which one will exist and which one will go? Tell me. Quickly answer me. Out of these two field components, DEY and DEZ, which field will be present and which will go, which will vanish? I hope you remember the derivation. Okay, EY exists, Tayyaba, very good. EY field exists and EZ field will get cancelled. And I had even given the reason also. Somebody has even given. Okay, Mehtab has answered Z. What is that Z? Whether it exists or Z eliminates? I hope Z you're talking about the cancellation. Yeah, Z eliminates. Okay, Z will go out. It will get cancelled. Y will remain. Okay, very good. Mehtab and Tayyaba. I had even given you the reason why this component will cancel out, because if you just see, it is parallel to this axis, and the point which we have considered here, and the wire, the way we have placed the wire, it is symmetrical. Okay, half portion is here, half portion is here. So if you take this point, if you find some field here, the Z component, a similar kind of Z component exists here also, but with a negative sign. So whatever components are present on the upside, even at the downside, for each of those areas, some component will exist. They both will be equal in magnitude, opposite in directions. Negative signs will be there. Due to this field component will eliminate. Okay, this was the reason which I had given you. So in short, remember, point is on y axis, so y field exists. In short, okay, just to remember, point P where we have taken, it is on y axis, so only this component will remain, this will go. Okay, because this concept we will be making use in sheet charge, so I just recalled you. Okay, so let us start with this derivation. Field due to a sheet of charge. As I told you, we have to consider a sheet of infinite dimensions. That's why you can just, these waving lines, okay, they indicate extension on both sides. So it's an infinite sheet of charge. Let us consider a charge sheet. Actually, this should be completely filled with charges, okay. If I fill completely the sheet by positive charges, remaining alphabets will not be visible to you. So I did not do. But what you can do, just to fill this complete background, this sheet by pencil. If you are doing it in your notebooks, just to make sure that it is uniformly distributed charges it is having. I have not done anything here. I did not shade also, but at least shade or put all these positive marks indicating there is a charge distribution. I did not do it because if I do that, those charges and all these whatever I have written, they all will get mixed up and you will not understand. So I did not do it. So it is placed in the space as shown. If you see, this is just like, if this is, just a second, I'll draw it here neatly. Okay. Something like this, a cube. Okay. Assume that this is your classroom. Okay. Some space, square, some square or rectangle or whatever, cubicle or cuboid. Okay. Your classroom is there. This is the edge of your classroom. Okay. This is your floor. This is the floor on which your desks are there. You stand, you sit. Okay. Here in front of you, teacher stands. Here is the green board. So this wall represents what? If I take this, these are the edges. Okay, corners are there and the edges are there of your classroom. Y axis, X axis, and Z axis. So this board where it is hanged and the teacher, in front of this, the teacher will stand and deliver the lecture. This background wall, this is actually in the YZ plane, right? So there are actually how many planes? XY plane, XZ plane and YZ plane. Out of this, the background wall is in YZ plane. Why I am telling this is because if you see this sheet is actually looking like a background. Okay, no doubt some part is coming out in both, but main is that this background where your green board is mounted. Okay, so it is indicating it is in YZ plane. Okay, don't think that it has come out, so it is actually in XZ plane or XY plane. No, just the sheet as it is infinitely extended, it is shown like that. But however, the sheet is placed in YZ plane, background, where your teacher stands. So consider a sheet placed in the space as shown. Let P be a point on X axis. This one. Shall I zoom it a little bit? It is a bit more clear to you. Okay. P is a point on X axis. Okay. I have taken X axis. Similarly, you can take any other axis depending on in which plane you have kept the sheet. For example, in your classroom, if this is your side wall, okay, and if the sheet is mounted somewhere here, so the sheet is kept in XZ plane. In that case, the observation point will be Y. Okay, the third axis will be your observation point. And similarly, if this is the floor where you have kept the sheet, okay, so it will be in XY plane. The sheet is totally in the floor. Under that case, this Z plane, the Z axis will have the observation point P. Always the plane in which you are keeping the sheet, other than that, whichever axis remains, that will be your observation point. Okay. So let P be a point on X-axis. Now I hope you know why it is on X-axis only, because the plane which the sheet which we have placed, it is in YZ plane. So the third axis remaining is X only. So at point, the point P is on this X-axis. This is the observation point. P is the point on X-axis where we need to find this electric field intensity. Okay. Now, what we will do, just in case of volume charge, what we did, we took some space. Inside that, some cube we considered at some point M. This was the observation point. Then by doing some manipulations, we found out electric field in terms of rho v directly. Similarly, in case of line charge, what we did, we took a straight long wire. Some observation point was here. Taking some part, we manipulated something. We used some triangle and everything. We found out E in terms of rho L. Okay, the equation has rho L, the equation has rho V. Now, as we know that, as it is the sheet of charge, we will have the field expression E in terms of rho S. Okay. But what we will do, instead of going again by a new method, we will make use of the existing. That is, we have certain relationships between these rho L, rho S and rho V. We have the relations. I will tell you what are those relations. Based on those relations, we will make use of this rho L, which we have just in the previous session we have derived. E is equal to rho L divided by 2 epsilon naught something R. So that expression has rho L. We will make use of the previous session's output, what we got in this, to find out rho S expression. Okay. So we will not again go by a new method. Existing, the previous session's discussion, we will make use in this rho S. Yeah, remember this. So let us consider, that's why as we have to go with the surface area, okay, because rho S has to be found out. Like we should deal with rho S, surface charge density. But if you see here, let us consider a thin strip line we are considering. So you might wonder, we have a sheet of charge. Okay, we should have taken the sheet and rho S, small part of it, applying the integration. We should have done all those things. But as this complete sheet has got many strips like this, okay, many strips all together will become a sheet. Okay, many lines together will become a sheet. What we will do, instead of taking one small area in that, we will take one complete strip. It is indicating a line wire. Okay, one strip in the complete sheet. So अगर ऐसे बहुत सारे sheets आप मिला लेंगे, okay, if you join many sheets all together, you will get a complete sheet of charge. Okay. So that's why in order to derive this further, we will use a thin strip. Strip indicates what? Just assume it as a wire. Okay. Now, this is important. Just now I have already explained you. Since the sheet is in YZ plane, okay, we have kept the sheet in YZ plane, and the point P, it is in X direction. It is along the X axis. So what will happen? Just now I have explained you, whichever point you are considering, whichever axis you are considering at which point P is there, only that component will exist. Remaining two components will cancel out. Okay. Just I'll recall this expression as this is your y axis. Point is on y, only dy component exists. Dz will cancel, right? So similarly, if you take here, the point considered is on x axis. So if you resolve this into components, this is actually the field direction E. If you resolve it into many components, Ex, Ey and Ez, out of which point is on x axis. Hence, this y and z component will cancel, only x will remain. Okay, shortcut method to remember. Here is the details are given. The one field will be like this, whose magnitudes are same and opposite in directions. They will cancel out. One more field is again like this, same magnitude, opposite direction. They will cancel out. Only the x component, okay, where the point P is there, they both get added up. Hence, only Ex part of your complete components, Ex, Ey, Ez will remain. Ey and Ez will eliminate, only Ex will remain. Okay. Due to the symmetry, because of the symmetry, y and z components of the field due to the differential length will cancel out, and only x component will remain. Remember, अगर आप sheet यहाँ पर रख रहे हो, point x पे आएगा, so only Ex will remain. Now, if I put a sheet sheet here in yx plane, that is xz plane, then point will be somewhere here on y axis. So that time only Ey will be present, remaining two will get cancelled. Now similarly, if I keep a sheet somewhere here in xy plane, so point of observation will be on the third axis, point P. Under that case, only Ez will remain, remaining two will get cancelled. Okay, this is the thing what I want to tell you. So sheet is in YZ plane, so obviously x will remain. So x axis pe point rahega P. That's why only x component of the field will remain. Now this is already we have derived. See here. Finally we got E is equal to rho L 2 pi epsilon naught into R unit vector Ay. Why? Because only y component exists, point P is on y direction. So we will make use of this equation. See, we know that already for a line charge, electric field intensity is dE is equal to, actually it was dEy, but don't take here Ey because here the components are getting changed. So simply take dE. Now, why dE? Why not complete E? That may be the question. We are discussing, no doubt, for a complete strip, for a complete wire, this is our expression E, capital E. But if you take this complete sheet, this sheet has got many such lines, many such strips are still present. So we have to integrate all together. For that, one single wire is dE only for us, for this discussion. So it will become dE, not capital E directly. So this is the already derived expression, we know it. Now let us see what is the relation between rho L and rho S, because we have to find rho S in terms of E according to the heading, field due to a sheet charge. But we have this expression already. So we will see what is the relation between these two and we will substitute that. Rho L is the linear charge density, which is charge per that particular element. Element is length here, Q by L. And rho S is the surface charge density, which is given by the charge by the element. Element is the surface. Similarly, if it is volume charge density, it would have been Q by V, volume. So according to that, if I write this Q by S, surface area of the line, that is area of this strip, how will you find the area of the strip? I did not explain you the figure, right? Only I showed you the point P. So let me continue this afterwards. I'll tell you the figure. Sorry, point P, I have explained you. We have considered the point P on x-axis. Then plane is on, it is kept like a board, green board in the classroom. That is YZ plane we are using. If you observe, this is x direction, and from point P to origin, this distance is x direction. So I am using small x. Okay. And similarly, this is in y direction. So I am taking this y. Okay. No doubt this y, it may extend depending on the sheet size. But here, as for now, this is your y and this is your x because of these two lines, x-axis and y-axis. And from the point P to the strip, if this is the distance, point P is where we want to find the electric field. Okay. So this is your wire. From the center, try to drag it. You will get a position vector capital R. And this value is given by, you can apply either Pythagoras theorem you can apply here. See, this is your theta, making some angle theta, and this is your 90 degrees. So if this is your 90 degrees and this is theta, this is your base, okay, adjacent, and this is your opposite. So this is your adjacent, this is your opposite. Hypotenuse is adjacent square plus opposite square. R square is equal to x square plus y square. R is equal to square root of x square plus y square. Pythagoras theorem you apply. This length of adjacent is x, length of opposite is y. Taking that, R is calculated, and point P's coordinates, it is very much clear. As point is on x-axis, values are x, 0, 0. Suppose if I have a point P here, what may be the points? 0, y, 0. And similarly, point agar z axis pe hota, so you would have taken 0, 0 and z. Okay. This is about the figure, and rho S is the this sheet, complete sheets surface charge density. Okay. Now I have explained you the figure. You can see here these two angles are same. Okay. What kind of angles you tell this? You tell me what kind of angles they are. If this is the case, these two angles are same. Anyone? Which kind of angles they are making? Why I have equated both? No one, I guess. Yeah, you can Google search and tell me later. Okay, I have explained you the figure now. Coming back to the discussion, we want to have a relation between line charge and surface charge, because we have already this expression derived in the previous session. We will just replace rho L with the rho S. Then we can continue the derivation. For that, rho L is charge by length, rho S is charge by surface area, or if it is a volume charge density, rho V is equal to Q by V. Now, I can write the area of the sheet. How? You see, if you see the strip, this strip, the area is, the thickness I have considered smaller value dy. Okay, dy is the thickness. Dy is the thickness, and if I assume L as the length of the strip, you can just take this here. You just denote this as the length L. I have not marked, you do it. If I do that, this is your length, this is your width. L into dy will give you the area of that, right? So I can write the area for that sheet as L into dy, length into width or thickness. And Q by L is actually rho L. So substitute that rho L here and dy, keep it as it is. So rho S is equal to rho L divided by dy, or rho L is equal to rho S into dy. So I have an equation for dE in terms of rho L, but rho L I can express in terms of rho S. So I will simply substitute it. So taking only the x component, I have explained you why only x component. Point is on P, it is on x axis. Consider Ex only. Ey and Ez will get cancelled out. Only x will remain. Because of that, we are considering only x component. So Dex will be rho L, instead of rho L, I will put rho S dy 2 pi by epsilon naught into R. Why I have changed this capital R? If you see the figure, the distance between the strip and the point is capital R. So I have changed it according to my figure, the sheet charge figure. Accordingly, I have changed it. Now you wonder why I have considered cos theta here. Okay, see here. Okay, if you take here, let me draw this. It looks something like this. This is your point P and this is the angle theta. If that is the case, then this is your field E. This is your x direction. If you make a triangle here, okay, point P's coordinates you already know, x, 0, 0. According to this, this is your 90 degrees. I want x component of the field, right? E suffix x. E suffix x, x component of the field. So if I resolve this E into two components, say Ex and some other two components which I don't want, they are already cancelled. I want only this part, okay? I want only this line, this component of E. It is actually Ex. Now, what is this? This is actually, if you observe, you have a 90 degree here. This is your theta. Theta. I want this length. Okay. So this is your opposite. This is your adjacent value. This is your hypotenuse value. Okay. I have just rotated the structure like this. This is your point P. So this is adjacent, okay, or the base, which is actually cos theta. That's why as I want Dex, only x component of the field, I have to multiply this all value, whatever is there here, this value with cos theta. Remember, because I want Ex component. If it would have been Ey component, suppose you would have got Ey component, that time probably I may needed this, okay, which is probably opposite. Opposite is sin theta. I might have used some other terms there. But here I wanted this resolution. E is here actually. If I resolved into 2 components or 3 components, other 2 I don't want. I want only Ex component. X component means this line. This line is your cos theta. Okay. So you just multiply it with cos theta. Then rho L divided by 2 pi epsilon naught into R. I have kept it, instead of rho L, I have substituted rho S into dy. I have substituted. And what is R? In the figure you can see. Where is it? R is square root of x square plus y square. So I have substituted R. And what is cos theta? From this triangle, try to find cos theta. This is your 90 degrees. This is your angle. So this is your adjacent. This is your opposite. This is your hypotenuse. Hypotenuse. So cos theta is equal to adjacent by hypotenuse. What is adjacent? Adjacent is x. Hypotenuse is capital R, right? X by R. Substitute that, x by R. R value just now we have calculated. X by R, which is equal to x by square root of x square plus y square. Pythagoras theorem. Now, as I told you, if you are considering a sheet, one strip you have considered, such there are many such strips in the sheet which will all together will make a single sheet. That's why to get the overall field, we should go for integration. Integration of this above equation to get the complete sheet electric field. Since the strip is an infinite strip, and the field due to this entire strip, entire sheet is actually the sum of all the strips. So Ex will be integration of dEx. So just integrate it over minus to plus infinity. Why minus to plus? You can see here I have shaded this zigzag indicates it is an infinite sheet. So the dimensions we will consider as infinity. So from minus to plus infinity, this complete equation we will integrate. See, these square roots will go, half plus half will be 1. So the power is 1. Now, this is a constant term, keep it out. What is the integration of this? I think you know this already. Integration of x by x square plus y square is tan inverse of y by x. This formula you might be knowing. If you don't know, you go for substitution method. Y is equal to, substitute y is equal to x x tan theta. You substitute that, you will get it. Okay, substitute y equals to x tan theta. Then you simplify this just like the previous session how we solved. You will get this tan inverse of y by x. Apply the limits minus to plus infinity. When tan is infinity, it is at 90 degrees. So it is pi by 2 minus of minus pi by 2, which is equal to pi. Pi will get cancelled. You will get Ex is equal to rho S divided by 2 pi epsilon naught. This is the field you get. But if you see here in the final expression, we have Ay also. But here I have not taken that Ay anywhere. See, that's why as the field is a vector quantity, we want direction, we want unit vector. Because of that, I'll consider A as the unit vector. Okay, nor directed normally outwards. That I'll show you how it is. Then the field E is whatever this expression is there, just associate a unit vector. And E's unit is volt per meter. So if you observe, final expression has got rho S in the expression. Okay. As a note I have written, E is dependent on rho S and epsilon. But anywhere, whether the distance is maintained, what is the distance of this sheet? If I assume if here is a sheet and here is a point of observation, I don't know what is the distance between them, but E is fixed. And if I just change the point to here, the E will be fixed. That is, E is independent of the distance of the point of consideration. E is fixed in magnitude and direction. Rho S is a constant term, hence E remains the same. whatever may be the distance from the infinite sheet of charge. So point आप कहां पर भी लो कंसिडरेशन E का फाइंड आउट करने के लिए डिस्टेंस इंडिपेंडेंट रहेगा, E वैल्यू फिक्स्ड रहेगा. Here I have given you